In this video, I'll show you how to build and train a neural network model for remote sensing image classification in Python. We'll cover everything from installing and importing machine learning libraries to visualizing and saving the results. By the end of this video, you'll have a deep understanding of how to use the power of machine learning to classify remote sensing images with ease. Let's get started.
Alright, so now we will do Landuse Landcore classification using neural network. But before that, make sure your computer has Python installed. We will need Python 3. Python 3. So we can download Python 3.11 directly from this website, python.org/downloads. Or if you want 3.10, you could download it from here and find the appropriate file for your Windows version. And uh, this is Windows 64-bit. For me, this will be the correct file. Just select this and this will download. Double click this and follow the instruction. Make sure you add the Python to path variable so that you can run Python from command line. All right, now let's start. So we have already downloaded all the data from this GitHub repo, and we also have downloaded satellite image from this, and we have kept all of them in our folder. So we already have training data. We already have our training data converted to raster. So now we will use Jupyter Notebook to run all the code for doing classification using neural network. So just navigate to that folder. Here is the Jupyter Notebook. So from here, hit CMD, it will open the command line. So now let's verify if we have different packages or not. So just do Python mpip install numpy. So requirement satisfied. Matplotlib already satisfied. TensorFlow already satisfied. Jupyter Notebook, just notebook, already satisfied. And let's see if we have GDAL or not. But installing GDAL is a little bit of workaround, so we need to download a GDAL wheel file. So just go to Google or just go to your browser and type GDAL wheel and go to this website. Control F, GDAL. So find the GDAL file for your appropriate for your computer. So this is the Python version and this is the computer architecture. So for us it will be 3.0 and 64. Just download this, place it somewhere appropriate, and you could just wait for the download to complete. And here you could cd there. It will be c/users/ or instead of typing all that, we could simply open the command line here. All right, and say Python mpip install and hit tab to get that name and install. So GDAL is already installed. So now we have all the libraries we require for running the notebook. Just go back to the location with your notebook and open the terminal there and run the Jupyter notebook by hitting Python and notebook, or you could simply run Jupyter notebook. Now it will open the Jupyter notebook on your default browser. Open the notebook. We have already covered the part 1 and part 2 here. Just to go to part 3. We also right now install the libraries, so we don't need to do them now. Now we will have to import all the libraries required for carrying out this exercise. So OS is for changing directories, NumPy is for manipulating numerical arrays, GDAL, that is within OSGeo, it is for reading and writing raster files. Matplotlib.pyplot is for visualizing image and graphs, and this listed color map is to provide a different color to different classes in our classified image. The TensorFlow will be used to create, train, and test the model, neural network model. We will use sequential model with different dense layers, and we will use linear, ReLU, and sigmoid activation wherever appropriate. And this line here is for reducing the amount of text printed from running different codes related to TensorFlow. So just run this by hitting Shift Enter. It will import all the libraries, then hit enter to change the directory. So mostly this directory will be the location of the notebook. uh, the default directory will be the location of the notebook, but if your data is in the different directory, just provide that folder path here. And this is just for reading our satellite image data and the training data we prepared in the previous lesson. So here just convert them to NumPy array. See the size of x and y. So here we can see 6 band, this number of rows, this number of column. This is single band, this number of rows, this number of column. Now we will want to move this number of band to like third axis. So we will do that by running this move axis method. So we can see the number of band is now the third axis. And we will also receive this on a nice tabular form. So this 6 band will correspond to 1 column each, and all each pixel will correspond to 1 row. So this is the code to do that. We will similarly receive the output y, and now we would like to remove the data with no data value. So let's see what value represents no data here. So no data is represented by value 15. We could also see that from ArcMap. So let me quickly open ArcMap because we will need it later. While that's opening, we will want to get data only on the places that has value. That means that place is not no data value. So any location with value not equal to 15, that will be our data index. And we will grab the data from those locations, those rows. And let's see how many classes our output clean white clean has. So there are 6 classes, 1 through 6. But arrays in NumPy or generally in Python, the indexing starts from 0. So we'll just convert them 0 to 5 by subtracting 1 from each value. So now we can see it ranges from 0 to 5. Let's quickly open the ArcMap and let me quickly have a look at the satellite image. So not the satellite image, and the white train. All right. So for white train, we can go to properties and source raster information and see no data value is 15. All right, now we have verified that. We can continue. So generally it is a good practice in machine learning to keep a separate set um, of data for validation purpose. Generally that is called a development set, but sometimes people call it test set, which actually is different, but we will simply continue calling it test set. So this step will uh, split our clean data into training set, which will be 80% of the data, and validation or test set, which will be 20%. So we are using NumPy seed to seed 0 to make the result reproducible. Now we will just run this code so that 20% of our data will be in test data and 80% will be in validation or test data. So 80% test data, sorry, 80% training data, 20% test data. And we will just grab the values and see this is the shape of our X train, Y train, X test, and Y test. Now let's see how many unique classes are in our data set. So in training data, there are 6 unique classes, and in test data also those 6 classes, and the number of examples in both the sets, they look proportional, somewhat proportional. So this is not skewed that much. All right, so now we have our training data and test data. Let's build our model. So we will also set a random seed for TensorFlow, so that model will be same every time we run this cell. And we will use the sequential model we imported earlier. And there are two important things. So first is the input shape. It corresponds to the column we have in our input data. So our xclean had 6 columns, so this number is 6. And here this number represents how many classes we want in our output data. So our output data y has 6 unique classes. So this corresponds to 6. And these two numbers are arbitrary. We could use different number and even get maybe even better model, but we are just using these for simplicity here. So after we build the model, we make a model, we will build the model and get the summary. So there are 3 dense layers, these many parameters, overall 661 trainable parameters, which is not that much comparing to deep neural network, but it's not that bad amount. All right, so to train the model, we'll have to first compile it. So to compile a model, we'll have to set its loss function and its optimizer. So we will use sparse categorical cross entropy as a loss function and Adam is our optimizer. These are good options mostly always for multi-class classification. And we are using model.fit method to train the model. So it will fit the model, meaning train the model, and we will see each of the examples 40 times. And that is the number of epochs. If we increase the number of epochs, it will take a long time to train the model, but it might improve its accuracy. I'm not going to run this code here because it takes around 3 minutes to run, but um, I already have trained that model and saved it. So you could run that model and go for and wait for 3 minutes or more depending upon the machine, and then visualize the loss function. So here we can see the loss initially decreased rapidly, but later it somewhat flattened out. We can see the trend, like if we train it more, the loss could go on decreasing for some time, but we stopped early because it takes a long time to train for more epochs. So here I will just load the model. So if we have trained our model, we wouldn't want to retrain that model if we just want to make prediction later, because training takes a long time. So we can simply save the model by running this code here, but I don't have a model to save here. I will simply load the model. So this model is in my working directory. So I'll just simply hit this line to load the model. So this is my model here, loaded. You don't have to load the model if you haven't saved, because you have the model from the direct training here. So now we have trained the model and saved it. We can make the prediction using this model here. So we will first predict for the trained data. It will be quick. So I'm running this. So this will give for each row in our training data 6 numbers. So that number somewhat correspond to probability of belonging in one of the 6 classes, each of the 6 classes. But those numbers should be converted to a value between 0 and 1 using softmax. So simply do that, and we will assign each row to the class that has maximum probability. So just run this cell, and we can see how many of the training, uh, what was our accuracy, training accuracy, by comparing the predicted result with the actual training classes. So simply run that, and to evaluate the model, we will do simply same things but with the test data. So simply run this cell, and now we will print out what is our training accuracy and test accuracy is. So this is 93.81 and 93.75. Both of them are pretty close. That means we don't have a high variance problem. We might have more high bias problem if our desired or state of the art accuracy is like 95%. In that case, if we want to increase our accuracy, we could train a bigger neural network, and that that would help us with our low accuracy. All right. And training for a longer time or more epochs or using more variables also can help with reducing the bias. Now, if we want to predict for the entire data, it will take some time. So I'll just run this and explain the code below. So it will simply do what we did with xtrain and xtest, but it will do for the entire image. And this will generate same 6 numbers for each row that correspond to each class, and we will convert them to values between 0 and 1 using softmax. And we will also assign each row to the class for which it has a maximum probability. Excuse me. And as we remember, we earlier subtracted 1 from the training classes. So now those class values range from 0 to 5. So we will just undo that by adding 1 to the predicted class. This will simply balance out things. And we have to reshape these y predicted, because this y predicted is one dimensional. As you can see here, we have to convert it to 2 dimensional, which will be the same size of the YDS data. So we will just simply reshape it. And to visualize the data, predicted output, first let's define the color map. So these 6 colors correspond to 6 classes, and we will simply plot the y-pred using this color map, and we can see that it is a good result here. And if we want to predict, if we want to see what our prediction using maximum likelihood classification was, we could simply read that file and convert to array and plot them using the same color map, here. And this is the result from maximum likelihood classification. Now we could also visualize them side by side for better comparison. Here, one noticeable thing would be these areas are classified as urban by maximum likelihood classification and as agriculture by neural network. So we can visually compare them later on ArcMap. For other things, other noticeable thing here are these are sand areas classified as urban. Here also there is that problem. So there are certain classes which cannot simply be which are hard to separate from each other, like urban and sand. We might need to do some band selection or use different variables that help us to separate those classes, but that is something beyond the scope of today's lesson. We can explore those topics in the future. All right, so after this, we can save the predicted result using this code. So first, this will simply get a driver for GeoTIFF and create a GeoTIFF file with this many columns and this many rows and this many bands. So these are all the exactly same as that of our input uh, image, and we have to write that our YPRED array to this band, the band one of this file. And we have to also set the projection and geotransform. We will just get the geotransform from our original satellite image, the projection and geotransform from the original image, so that those images will be, so the output image will be on the correct geographic position. And we need to do these two things. So we will need to flush gauge the raster band as well as the file so that this file is released and can be opened in another software. So after we do that, we can open that image in ArcMap. So this is classified using maximum likelihood classification, and this is using neural network. So just simply load both of them, uh, and let's change the symbology here. So first is water, so blue, I guess. Second is sand, all right. Third, let's see. What is the third one? Third is forest. So forest. What's the fourth one? Grass. Let's see. Grass. And then cultivation and built up. So this should be yellow and this should be red or better red. All right. So I will simply change its symbology as well by importing. So import from this file. All right. So now both of these have the same symbology. Let's compare which one did better. We will just do a quick visual comparison. So this area, let's see what this area should be. So this is agriculture, not urban. So maximum likelihood did a poor job here. Neural network did a good job here, but still it can be better if we provide more training examples here. All right, and also that sand and built-up area problem, we could see that along this river. So neural network did a bad job separating sand from urban area. It seems maximum likelihood did a better job, but still there are a lot of misclassified sand areas as urban areas. So I hope you gained some knowledge about using ArcMap for data preparation, Python for neural network classification, and I hope you can use this for for your future projects or your work. Let me know if you have any comments or suggestions, and I will try to address them. Thank you and good luck on your learning journey. Before going, I will like to show you if the if the prediction was done. So where were we? We just did prediction for all the data. We'll provide softmax, predict, change back, change to array, visualize like this. Just quickly run all of this. So this is basically the same. So nothing is changing here, and this will simply save that. All right. See you.